Good morning, everyone. Thanks for being here. Thanks for the invitation also to present today. As I get set up. So indeed, I've been to this summer school before. This was when it was like 20-ish people in Toronto. This is where I met a lot of people who are now, world-recognized researchers, many of them professors at faculties in Canada and elsewhere. And so I really wish you all a great week. I think it's a great opportunity to make the most of it. The goal today for my time to speak is to do sort of an intro to basic neural networks concepts. I think probably you're familiar with a lot of it, so I will go fairly quickly over these ideas and these concepts. Do raise your hand if you have questions. We're going to try without the mic, so just shout your questions and I'll repeat them for everyone. And then I'm happy to make this as interactive as this needs to be. And without further ado, let's start, because apparently I'm already 20 minutes in my presentation. All right, so let's talk about neural nets. I will say that a lot of what I'll talk about is taken from my online course. So if you want to go through these ideas much more slowly, you can go check it out on YouTube, where a younger version of myself is presenting all of that material. You can also look at the CIFAR lectures of previous summer schools. Most of these are online. For my lecture, you probably want to go 2 years ago. For some reason, the one last year doesn't have my slides. It's just me speaking. So 2 years ago, I covered more or less the same material. So if I'm going too quickly and want to go to it again, please do that. That material from 2 years ago is already online. All right. So I sort of have two parts, but I probably won't really take a break and do the two parts fairly quickly. In the first part, we're really going to go through fairly basic things that you should know about when it comes to neural nets, what's forward propagation, what's backprop, and then some more recent ideas in deep learning, or let's say for the new wave of neural nets research that we call deep learning, like unsupervised retraining and dropout and so on. But I will go fairly quickly just to get a sense of where people are. For instance, like if you raise your hand if you know about backpropagation. So I think that's like almost everyone, which is sort of what I expect. I will still go through these ideas very quickly as a refresher, but if you have questions, please don't hesitate to ask it now or even later on, because I'll stick around at the summer school. For instance, I'll be there tomorrow also most of the day. So let's get started. So we'll first start talking about what is a neural network, how do we make predictions with a neural network, and what kind of predictions can we make with neural networks. So to do that, we first need to start talking about what is a neuron, because an artificial neural net is going to have artificial neurons. So a neuron, an artificial neuron, is first going to have something I'll call a pre-activation. And a pre-activation is just going to be a linear transformation, so a bias, and then a weight vector that multiplies some inputs to that neuron. And then we're going to compute the activation, or sometimes I'll say the output of that neuron, by applying a nonlinear function, g. And so really a neuron is characterized by the set of weights that goes into the neuron and that multiplies the importance of each of its inputs, a bias that sort of gouges the default activation of that neuron, and then some activation function that introduces nonlinearity in the neuron. So, and the parameters of that neuron will be the weights W's and the bias B. So visually, what does that mean? Well, for instance, if we had a neuron connected to two inputs in 2 dimensions, input x1 and x2, well, the weight vector would sort of correspond to what is the orthogonal direction of a ridge between an area of input space that has high activation and another area in input space that has low activation. Okay? And then the bias, if you were to change the bias keeping the same W, you would just change where that ridge is that separates the high activation and low activation regions. So you can sort of think of a neuron as kind of a classifier. If I apply the threshold on the activation, I could essentially classify everything here in one class and everything here in another class. That's what a single neuron allows you to do. But then we can start combining these neurons to have more complicated decision functions. So for instance, if I sort of took this neuron here and then subtracted the activation of that neuron, you can see how essentially that area here would be taken off this part here, and so you would get something more like this, where it's no longer just a linear separation between two areas. You now have this band of high activation and then two on its side, 2 areas of lower activation. So visually, you can start seeing that if I did this, but in both directions in 2D, so if I had these 4 neurons here, then I could probably intuitively combine them to get something more like this, where now I have just a little area, isolated area in 2 dimensions where I have high activations and everywhere else has low activations. Which kind of means that by combining in 2 dimensions 4 neurons, I can sort of arbitrarily have an output in an isolated area of the input space. And then building on this, that means that I can essentially, by having in 2 dimensions combinations of 4 neurons positioned in the right way, parameterized in the right way, I can carve out sort of arbitrarily complex surface areas and decision areas. So for instance, if I have a class 1 represented by this character here and class 2 here, well, to achieve a classifier like this that classifies things differently in this area versus that area, let's say this is the class 1 with high activation, then I could sort of position a bunch of little bumps like that with essentially 4 neurons together and put one here and so on to have this more complicated decision surface between one category and another category. So by combining many of these individual neurons, we can represent fairly complicated functions and make fairly complicated classification decisions on some input data. And theoretically, this was characterized in particular by Hornick in this theorem, which I'm paraphrasing here. A single hidden layer neural network with a linear output can approximate any continuous function arbitrarily well, given enough hidden units. So if I have enough of these small units, I combine them linearly, I can have as complicated a function as I want. Which essentially means that if I put enough neurons in my system, in my model, then I can represent pretty much anything. It's only continuous function, but still, that's a really large class of processes, of functions, of outputs that I would want to model. Now, this says nothing about how do I find the configurations and the weights of these neurons so that I get any function that I want. It just says that it exists. And it's kind of satisfying. It means that if we only consider neural nets to represent functions, that we're not giving away much in terms of what I can represent. I can represent pretty much any function, even with just a single hidden layer. Okay? And that's part of the motivation for focusing and concentrating on using neural nets for doing machine learning. Okay. Any questions about that or comments? All right. Okay, so remember, we can represent pretty much any function with neural nets, even with just a single layer. But actually, we will oftentimes want multiple hidden layers. And so here, I'll present what is effectively the sort of basic parameterization that I'll use mostly through my presentation of a multi-layer neural net that has L hidden layers. So in this neural net illustrated here, at the bottom, I have my input layer. So if I'm classifying images, this input would be the pixels, the pixel intensities of all the pixels in an image. Here, I happen to have 2 hidden layers. And then this layer at the top is the output layer. And much like I mentioned, each neurons are essentially a linear transformation followed by an activation function. But now in each of my layers, I'm going to have multiple hidden units. And so the way I'm going to compute their activation is that I will take the pre-activation first of a layer is going to be a bias vector that is added into a linear transformation, so multiplication by a matrix W, of the activations of the previous layer, where if you had the first hidden layer, the previous layer is the input layer. Okay, so the way I note this in my notation, h of k is going to be the activation at layer k. And so if this notation, h of 0 of x will just be x. It will be the input. And I'm going to linear transform that activation by multiplying by a matrix W. And this matrix W, all of the rows are essentially the connections going into all of the hidden unit in layer k. And I'm going to add to each, so this is giving me a vector, and then to that vector, I add the bias of each individual unit in that layer, and that gives me my pre-activation. Then after that, I'm going to get an activation of the layer by applying some nonlinear function g. And similarly, I'll do the same thing for the output layer, but here I'm distinguishing them because I will often use a different nonlinearity for the output layer, the one at the very top that produces the output that I want to represent. I'll most of the time use a different nonlinearity than for the hidden units that are sort of in between the input and the output layer. And sometimes the whole neural network, from its input to its output, I will represent as function f of x, where f of x is going to be essentially referring to the output layer of my neural network. All right, questions about this notation? Okay, so k is the hidden layer. I'm using exponentials to index layers. Here I have weights and biases for each layer. This is why there's an index with the layer. And then we have our nonlinearities. What kind of activation functions? You probably know most of these. One that's often used is the sigmoid activation function that corresponds to this function here applied on the pre-activation of the neuron. What effectively it does is that it takes the pre-activation that can vary from minus infinity to plus infinity, and it squashes that in between 0 and 1. So after this activation, my neuron's activation will necessarily be positive, but will not be higher than 1. It'll be between 0 and 1. There's also the tanh, or a hyperbolic tangent activation function, which has this more complicated expression. It's kind of like the sigmoid, but the exception is that instead of squashing its pre-activation between 0 and 1, it squashes it between minus 1 and 1. So it's lower bounded, it's upper bounded, and one thing to notice is when the pre-activation is 0, then the value of the activation will be 0. Whereas for the sigmoid, if the pre-activation was 0, then that gives you a default activation of 0.5. We have the ReLU, or rectified linear activation function. It's very simple. You take your pre-activation, and you look at what is the max between 0 and that pre-activation function, and that's the activation. So what it means is that if the pre-activation is positive, then the ReLU activation function returns the pre-activation. So it's linear when the input is positive, when the pre-activation is positive. And if it's below 0, then it returns 0. Okay? So it's bounded below by 0, but it's not upper bounded. Okay? And you can see it's piecewise linear also. So when we build neural nets that are using ReLUs, the function that ends up being represented is essentially a bunch of linear pieces stuck together. Yes?
This function is not strictly increasing in the
Oh, you're absolutely right. Yeah, it is increasing, but not strictly. Good point. It took 5 years of teaching this for someone to tell me that. So apparently it's a very subtle distinction. Kudos to you. Any other mistakes in my slides? Oh, no, again, yes.
Why this three particular functions from there are many CDF of the random variable can strictly increase only between 0 and 1. Why we choose the sigma?
Right. So why choose any of these? It's a good question. I don't think there's a very good answer. Some of the reasons might be that empirically, at least for the ReLU, we do find the neurons tend to be more sparse. So a lot of them are actually going to be 0. Sometimes that seems like a good inductive bias for your model to essentially have, you think of each of these neurons as being like essentially pattern detectors, and you kind of want them to either not detect anything or detect something to some extent. And this kind of represents this sort of intuition. And there's another reason, which is depending on the activation function you choose, the partial derivative of the activation function is actually a simple expression of the activation. That can have like slight, computational advantages. But beyond that, there are probably other activation functions. And in fact, there's been a series of papers, people proposing other approaches or other ways of parameterizing this function and arguing for why it might be better in certain cases. So I would definitely not, if there's probably more research to be done on what are the right activation functions. But these, we do have the universal approximation theorem that applies. And so in a sense, they're kind of sufficient. And a lot of the observation as to why ReLU is very popular, potentially because you get a piecewise linear function. Maybe that's easier to optimize. So there's something to take into account. Something that's annoying about the sigmoid is that, as we'll see sort of later, you can get saturation of the neurons at above or below, and that can create difficulties in optimizing them. So that's another reason for considering various parameterization of the activation function. But there's no like, super convincing reason why one would be strictly better than the others. Yeah. Great question. Okay. Now how about the output layer? So I'll focus on the problem of classification. So maybe we have an image of, if you're familiar with the MNIST data set, this would be an image of an handwritten character. It's one of the digits from 0 to 9. So we have 10 classes. And I want to know this image drawn by someone, is it a 0, is it a 1, is it a 2, and so on. So in this case, I would like an output layer that has 10 units, 1 per class. And I would like my neural net to essentially give me an estimate of what is the probability that some input image belongs to one of the different 10 classes, 0, 1, up to 9. And so I want a distribution over 10 possible outcomes. It's a 0, it's a 1, it's a 2, and so on. And the way we're going to get that is to use the softmax activation function, where we take the vector of pre-activation, so this vector of size 10, if I have 10 classes, I take the exponential of all of these numbers, and then I divide by the sum of the exponentiated pre-activation functions. So by construction, all of these numbers after the softmax, they will be positive, and they will sum to 1, like what we would want if we wanted to represent the probabilities of 1 out of 10 outcomes. Okay? And so oftentimes we will use the softmax for representing a distribution over classes in a classification problem. And then if we actually want to classify, we would feed in an input, and then we would look at which neuron has the highest value. So in other words, what is the estimated most likely class for that input? And then we would pick that class, and that would be the classification we would return if we were to sort of deploy a trained system that's performing classification. All right? And sort of all of these ideas, when you program them, oftentimes it's useful to think of your program as essentially a flow graph. We have different pieces represented in this tree here, where you essentially have, for instance, a piece that computes the pre-activation. It takes as input the parameters of that layer, and then it takes the previous layer, and then it would sort of, in your program, there would be some object or some sort of program structure that computes the linear transformation. And then we would have other blocks, or other objects maybe in your library that compute activation functions, so nonlinear activation functions. And you can think of coding up various neural nets as sort of putting these blocks together into a flow graph. And a lot of the libraries that are used right now, TensorFlow, PyTorch, and so on, use some version of this sort of conceptual idea in terms of how to represent neural networks with code. It will come in handy because it will make things more modular. It makes it easier to experiment with new architectures of neural nets. And also it will make it easier to compute backpropagation automatically. But I'll say a few words about that in a bit. OK, any other questions? Yes? Right, so I'll address that. Why, if a single hidden layer is sufficient to represent any function, why would we want multiple hidden layer? I'll touch on that later. That's a good question. Yeah. We hear about how just sticking a softmax as the output doesn't mean that this probability you're getting is calibrated or reflects the real sort of uncertainty about that label. But that's kind of where we're getting at with using a softmax. Yeah. Yes?
Would it make sense if we could learn these nonlinearities to change the amount of sparsity between different layers? The lower layers
Yep.
might have less sparsity and higher.
Yep.
Activates
Yeah, so the question is, should we try to learn the activation function? And some people have proposed ways of trying to do that. As far as I know, none of these ideas, they're interesting, but none of these ideas really in the end sort of bring much benefit compared to using the activation functions that I've shown. This is maybe partly because if you think of the second hidden layer, it is kind of composing, this hidden unit is going to be a really complicated nonlinear function of the input. So having already multiple layers is kind of like learning, a complicated activation function in multiple dimensions. So why is it that it's in the activation function specifically you want to do some learning versus over the whole function is not necessarily clear. And so now that said, I'm not saying that we're not going to find ways of learning just the activation function. And I think even people, there's this whole literature on automatic machine learning where people have been trying to discover new activation functions, I think maybe with some success. But if you use some that are there, you get most of the performance you need most of the time. Okay, I'll continue moving forward a little bit. So now let's talk about training these neural nets. How do I find the weights such that I have a good function, so a good classifier for my classification problem? Like a lot of machine learning, except Bayesian machine learning, which you'll hear about later this week or next week. So we will essentially frame the problem as an optimization problem. So what we will do is that we will define a loss that compares what are the probabilities that my neural net is assigning to each of the potential classes with what is the correct class. And so we'll define a loss that essentially will encourage assigning the most probability to the correct class. And then we will consider what is the average loss over all of my training data. So all of my data that I have, where I have the right input and the correct answer, what is the average loss? And potentially introducing some regularizer that will encourage certain values for my parameters. And I will think of training my neural net as minimizing this average loss plus regularization. Okay? So we cast the problem of learning as a problem, as an optimization problem, the problem of training as an optimization problem. So ideally, we would like this loss to be the classification loss. However, this classification loss, which would be, is the class with the highest probability the correct class, that's a loss that is not differentiable, and it will make training the neural net much harder. So instead, we will think of other losses that are essentially, sometimes we call them surrogate losses, that will take a sort of smooth form of the shape of what the 0-1 loss would take. All right, so we've converted the problem of training as an optimization problem. So then we can just invoke an algorithm from the optimization literature to train my neural net on my training data. And one basic algorithm that is used, or versions of which are used throughout in the deep learning literature, is stochastic gradient descent. Stochastic gradient descent works as follows. You start by initializing all of the parameters of your model. So in this case, it's all of the weights and all of the biases in all of the layers of my neural net, okay? Which I'm sort of illustrating here. So I find some way of initializing these parameters. And then for a certain number of epochs, where an epoch here refers to going through all of my training set once, I will iterate over all the input and target pairs of my training data. So I will iterate in my data over all pairs of, let's say, the input image and what class does this image belong to. And then I will compute delta, which is a direction in which I should update my parameters, all of my biases and all of my weights. And that delta in stochastic gradient descent is the descent direction of the loss plus the regularization term. Okay, so I'm going to want to compute what is the gradient. This is what this nabla term is. What is the gradient of the loss with respect to the index parameter of nabla, which is theta, which is all my parameters, my biases and my weights. And then I also incorporate the gradient of my regularization function, and we'll go through examples of what that is, with respect, again, to my parameters. And that's going to be this opposite direction of descent. So my gradient gives me in what direction I would increase the loss. I want to go in the opposite direction because I want to decrease the loss. That's why I have a minus here and a minus here. And that will be my delta, my update direction. And in stochastic gradient descent, all I do is that I take a step in that direction by adding to my current values of my parameter, alpha, which is often referred to the learning rate. Sometimes it's referred to as the step size. It's a scalar, and it's a hyperparameter, multiplied by my descent direction delta. And so I update theta by moving in that direction, and then I continue like this, going over the next pair, and the next pair, and the next pair, until I've done over all the input-output pairs of my training set, and that's one epoch, and then I repeat this, and I repeat this until I reach some criteria. And I'll talk about what good criteria are for that. And people who are familiar with this will notice that here I'm talking about the version that is looking at a single input and its target, but in practice often we use mini batches. And I'll discuss that a little bit more later. All right, so this is stochastic gradient descent. And so if I want to use it for a particular, to train a neural net, the pieces that I need to define that I haven't defined yet are what is the loss function that I'll use to compare my output layer with the real target, the output layer with the real target. What is my procedure for obtaining the gradient of my parameter, of my loss with respect to my parameters? And also, what is my choice of regularizer? And then also a way of getting the gradient for that. And I also need a method for initializing my parameters, my weights and my biases. So what I'll do now is go through all of these choices that we often make when training neural networks. Okay, let's start with the loss function. So intuitively, what do we want? We want that for some given input, we assign the highest probability possible to the correct class, the real class in which this input belongs to. And so I could try to just use as the loss minus the probability of the correct class, which means if I'm minimizing this, it's like maximizing the probability of the correct class. In practice, instead, we use the log of the probability of the correct class. In my notation, that means taking f of x, which is my output layer, so it's a vector, and then looking at the position corresponding to the true label y. Okay? So f of x of y corresponds to which neuron is the neuron associated with the true class y for my input x. And then I look at minus the log of that. So what that means is that if I assign a very low probability, so if f of x of y is close to 0, log of something close to 0 is a very large negative number, but then I have minus, so it's going to have a really high loss. However, if I give a probability very close to 1, if it was 1, log of 1 is 0, so I have a loss of 0. So it sort of satisfies what we want for a loss. High loss if I assign too low probabilities, low loss if I assign high probability to the correct class. Questions about this? Yeah. Yeah. Compared to doing what? Okay, so what's the benefit of doing stochastic gradient descent versus batch gradient descent? If you have a small data set for which there aren't that many examples, it's possible that batch gradient descent is perfectly fine. However, if you have a really large data set, think hundreds of thousands of examples, having to go through all of the examples to get one descent direction and do one update means that each update will be very, very expensive. And the fact is that after having looked at only a subset of these examples, let's say 100 or 1,000, you probably already have a good idea, if you just took those examples, of what is the descent direction that will improve your loss. And so instead of waiting to finish the whole data set, we found in practice that it's better to just use a small set of examples to get an approximate, so somewhat noisy estimate of the descent direction, do a step in that direction, and then move to the next examples. What that means is that when you'll have processed all of the data set, you will have moved much further away from your initial point than if you had waited until the very end of the data set and had done full batch gradient descent. Okay? So in practice, we do something kind of in between. We often don't do the extreme of just one single example. We'll have a mini batch of examples instead, 128 or something like that. Yes?
Would mini batches be better for generalization instead of doing a batch and overfit your data?
Hold that thought. We'll talk about that later. But some people have found relationships between that, yes. And it ends up being a hyperparameter, I should say. The mini batch, that's something you should probably try many different values. All right. Next, backpropagation. So my understanding is that most of you have seen backprops. I'll describe it fairly quickly. If you go at my YouTube video, I sort of derive each of these different steps, mathematically showing each of these parts. But essentially, what backprop is an efficient way of applying chain rule to get what is the gradient of the loss with respect to all of the weights and all of the biases in my neural network. And the way we do that is that we start by computing what is the gradient of my loss with respect to the index of nabla, which is we could start at the activation. It actually is convenient to go straight to the pre-activation of the output layer. And it turns out that it's this simple expression. The gradient of the loss with respect to the pre-activation at the output layer is minus E of y, which is the one-hot vector of label y. So what that means is, let's say in my problem I have 4 classes, and let's say that y is class 2, then it would be a vector with a 0, a 1, a 0, and a 0. Okay, so it's a vector of size number of classes with a 1 at the position corresponding to the class y. So it would be this one-hot vector minus the output, which is a vector of probabilities over classes of the current prediction of the neural net. So this is, for the true class, it's going to be 1 minus a number between 0 and 1. So for the real class, the position corresponding to the real class, I'm going to have a positive number. And all the others is going to be 0 minus a positive number, so it's going to be negative. So effectively, what this gradient is saying is that you should increase the pre-activation for the correct class. You should decrease the pre-activation for all other classes. And in particular, you should decrease it as much as you're currently assigning probability to. So if you're really certain it was the wrong class, you're going to have a much stronger gradient for pushing down that pre-activation. So intuitively, it kind of makes sense. That's kind of what you would expect the neural net would need to do. But now we need to take that gradient at the level of the pre-activation and send a signal to all the weights so that they know how can they all adjust so that this is achieved, that we're pushing down the probability of the wrong class and pushing up the probability or the pre-activation of the one correct class for that example. And so there we just invoke chain rule. And if you make the derivation, so what you end up doing is you have a for loop from the output layer all the way to the first hidden layer. So k from L plus 1 to 1. And we can start by first computing the gradients of the loss with respect to the weights and the bias of that layer. And that gradient happens to be, for the weights, it's the gradient of the loss with respect to the pre-activation times the transpose of the activation vector of the layer below. So this vector is going to be a column vector. The other vector transpose is going to be a row vector. When you multiply these, you're going to get a matrix of the size of the weight matrix, and that's going to give you your descent direction. Okay? The gradient for the bias is just the gradient of the loss with respect to the pre-activation, so it's very simple. And now I need to start sending gradients downwards towards the other layers below. So I can first start by computing what is the gradient of my loss with respect to the activation at the layer below, k minus 1. And that is also simple. It's just the gradient of the loss multiplied by the transpose of the weight matrix at that layer. So it's just a simple linear transformation of the gradient you had at the layer above. And then to get the gradient of the loss with respect to the pre-activation of the layer below, I take the gradient I just computed here, the gradient of the loss with respect to the activation, and then I do an element-wise multiplication, this is what this symbol is, by the partial derivative of the activation function for each neuron. Okay? So again, this is an operation. This is actually very simple. We have so before we had just a linear transformation, and then here we have this nonlinear transformation, which is just an element-wise transformation. So the backward pass is going to be about as efficient as the forward pass in a fully connected neural network. And the reason I still present it here is to highlight one thing, another thing, except that it's pretty efficient, has about the same complexity as the forward pass. It also suggests what are things that could happen that would make training a neural net difficult. We would have a hard time, for instance, training the first hidden layer if the gradients that came in were very, very small and essentially were close to 0 and provided no information on how to change the behavior of that first hidden layer. And ways in which this might happen, it could be if the weight matrix here is too small and close to 0. It could also be because the partial derivative of the activation functions is close to 0. And that would correspond to cases where the unit is saturated, where the partial derivative is close to 0. It means that the activation is flat at that level. And that's what we mean by saturation. And it's a bad thing because you're multiplying gradients by 0 when they go downwards, which means that it might lead to the layers below to have very weak signal on how to adjust so as to classify the data correctly. So those are things that we sometimes look at when we start debugging neural nets. Are my units saturated? How do the gradients look like at the various level? Are they sort of shrinking towards 0 too quickly? So those are things you sort of learn to do when you're applying and practicing neural networks. Any questions on that? Yes?
So when you're debugging neural networks for small gradients, would you be looking at the norm of the gradients? Or?
Okay, yeah, so the question is, what should we look at in terms of the gradients to sort of get a sense of whether there's a bug or something to be fixed? Looking at the norm of the gradient certainly makes sense. Like if it's too high, it can also lead to sort of instabilities. You could potentially look at whether all the gradients are aligned in the same direction. So if all hidden units are getting updated in about the same direction, this might be an indication that your hidden units are initially not diverse enough, not sort of doing different enough things in the space of hidden units. Those would be the two things I would mostly look at. Good question. Yes?
A little bit of a philosophical question when it comes to grading. You said
Yep.
that when we're computing these partial derivatives, they're actually partial derivatives for each of the individual variables.
Yeah.
That you want to change. Could it be the case that there is some sort of coordination problem where each, the gradient is telling you move this single variable a little bit?
Makes things worse for another, and yeah.
Yeah, or could it be the case that if you move both of them in the sense that you do when you supply the whole gradient, that you don't actually move as much?
Right. I think what you're referring to is the fact that when we make a step size in that direction, what we know, because it's the gradient at that location, we know that locally, if you follow that direction and you take a very small step, infinitely small step, you will be decreasing the function. You will be decreasing your loss. If you take too large of a step, this is where you might have something where it makes things worse in terms of the loss because you've now actually moved in a direction that is not good for that other weight vector, for that other neuron or that other weight. And then this is where you want to be careful about step size. You also maybe want to use a second order method that will try to take into account the shape of the loss and essentially take into account, is it locally convex or not? That might lead you to sort of avoid things that might happen like this. The easiest solution is more or less, if you find that the loss is actually going up, this suggests your learning rate is too high, and essentially locally the function is actually not very linear. That's a good question, and then the way we address this typically is playing with their learning rates. Yes?
Would it make sense sometimes to wait until loss goes a little bit up to maybe get out of a local minimum or something and then goes down again? This is the first question. Second
Right.
question is, does it make sense to use different step sizes for different layers?
Right, okay, so the first question was, if the loss goes up, should we immediately change the learning rate? Should we wait because maybe it's going to go down later? So we definitely tend to do this when we look at the loss on the validation set. This is something I'll talk about later, but I can say a few words about now. So later on, it's possible that due to stochasticity in the updates and so on, you temporarily go up in terms of error, but then later on you would continue going down. So oftentimes we use what I refer to as a look ahead. So we wait a few updates or a few epochs, and only if we've not done better for some amount of epochs do we then either stop training or sometimes we reduce the learning rate because we use that as evidence that our learning rate is too high. So having this kind of schedule is something that's used quite a bit actually. The other one, should we have learning rates that are different at different layers? Most likely, but there are methods for optimization that will essentially try to have that are better motivated in figuring out what should be the learning rates for different parameters. Things like Atom are doing that, things like Adagrad, and actually I'll mention it later when we get to that. Yes?
Are there techniques that try to understand the loss
Mhm. Mhm. So essentially, this is a question about how can we go beyond just trusting the gradient at the point we're at, maybe trying to get a sense of what the loss surface is like locally. Second order methods are a way of doing this. Other methods, if you use momentum, you're aggregating gradients across multiple time steps. This will give you some information to some extent. This might indirectly give you a sense that maybe there's like a valley that's quite narrow because then the gradients will cancel in those directions, but it will actually build momentum in the right direction. And I'm sure in the optimization literature there might be more sophisticated methods. But whether these apply to machine learning and neural nets depends on things like, do these methods scale to a large number of parameters? So here, the theta, the parameter vector in this SGD framework, so the total number of parameters is oftentimes in the millions. And there's a part of the optimization literature that never looks at high dimensional problems like that. They are much lower dimensional. So if you have a method that scales with that in a bad way, like not linearly, maybe you don't want to use those methods. Yes? Sure. If I'm going to talk about it? Yeah, later on we'll touch on some of these ideas, yeah. All right, last question before I move, yeah. So there are forms of second order methods that have been sort of developed in a way that they're adjusted to the large number of parameters, yeah. I think you have an optimization lecture by Jimmy Ba. I would be really surprised if you didn't touch on that. But yes, there are ways of exploiting the structure of neural nets where there are layers, it's not just a flat parameter, to do certain things that are second order like in a more effective and efficient way. Okay. Just looking quickly at the partial derivatives, I mentioned the possibility of saturation. So for instance, if you look at what is the partial derivative of the sigmoid, it conveniently is just the activation times 1 minus the activation. Okay? So what we see is that when the sigmoid is close to 0 or close to 1, the partial derivative is going to be close to 0. And this is where you get saturation. And this is where gradients are not going to flow through that unit. They're going to be more or less shrunk to 0. And it sort of reflects this, right? The partial derivative is sort of the slope of the tangent of that curve. And you can see as you get to the extreme, it is getting closer to 0. You get something kind of similar for the tan h, where the partial derivative, again, conveniently is just a function of the tan h itself. It's 1 minus the tan h squared. The ReLU is interesting. It's either 1 or 0. If the pre-activation is larger than 1, the 0, then the partial derivative is 1, and otherwise it's 0. So actually, when you're multiplying backwards, so when you're multiplying by the partial derivative, you're essentially multiplying by a binary mask, where either the gate is open or not in terms of the gradient flowing. This is potentially why we've had more success with ReLUs, for instance. The other methods will always shrink the gradient to some extent. It multiplies by something that's going to be strictly smaller than 1, okay? Unless it's perfectly saturated. And so that's potentially why, and this relates to the notion that maybe because it's piecewise linear, maybe that's why ReLU networks have been found to be easier to optimize. And in terms of programming all of this stuff, you can exploit this sort of structure that's more modular by essentially in your flow graph adding this longs function and then augmenting your library in a way for each of these boxes to also propagate gradients downwards. And then all you would need to do is to go backwards in that graph. And again, TensorFlow, PyTorch are using various versions of these ideas. Okay. Regularization, oftentimes we use L2 regularization, which is just penalizing the sum of the Frobenius norms squared, which is really just the sum of all of the weights squared. L1 is sometimes used also instead, so taking the absolute value instead of the square. L1 tends to favor having connections that are shrunk exactly to 0, whereas with L2 regularization, you're encouraging small weights, but you normally don't get sparsity from L2. And then the initialization, which is really important in neural nets. there are ways in which you can totally mess up your optimization with bad initializations. So in terms of the biases, oftentimes we initialize them to 0. One thing you can do for the hidden units is actually initialize them to negative values of the bias. You can even make that a hyperparameter if you want to encourage an initial sparse, a very sparse activation pattern in your layers. But otherwise, most of the time, biases are initialized to 0. The weights, now you can't initialize them to 0, especially with the tan H activation, because if you do this, then all of the activations are going to be 0. And we've seen, for instance, for updating the weights, the weight gradient is a function of the activation. So if it's all zeros, then the gradient will be 0, and you're essentially stuck at a point. You're not going to move out of it. We also can't initialize them all to the same non-zero value, because then you can show that all of the units are going to be updated exactly in the same way. So they're going to represent exactly the same function. But what you want within the layer is have different units that are doing different things, that are detecting different sub-patterns in your inputs that are useful for better representing your data and having an ability of classifying data in a nonlinear way. So what you need to do is find a way of breaking symmetry in the initial values of the units. And oftentimes what we do is initialize each of the weights either with a Gaussian centered at 0 or a uniform distribution within an interval. This interval here, which looks somewhat arbitrary, was actually derived such that I think for tan H activations, you will have at initialization variances of the gradients at different layers that are about the same. So this is kind of saying initially I would like the first backward pass to give me gradients that vary on about the same scale, so that all layers are updated in about the same way, or at least with about the same magnitude. But I think there are other papers that have looked at other proposals for ways to initialize. And I think what's called the Gloro initialization, because the first author is Xavier Gloro, I think is found in a fair number of packages. But even then, this was one guiding principle for doing this. There might be other initializations that work just as well or even better. But the key ingredients are you want non-zero weights and you want some amount of diversity. So you want to break symmetry essentially between these weights. Okay? Oh, yeah.
So there were some papers that were discussing the effect of initialization in a specific architecture that can limit the performance quite and affect the performance quite a lot. So also from experience, it matters a lot. I remember one of the ways explaining it was to initialize your weights close to or over the edge of chaos.
Okay.
Can you say
Well, I don't know about this piece of work, but I'm sure there are papers that have looked at what are good principles that are beyond just breaking symmetry and non-zero. This sounds potentially reasonable. I would just practically speaking, I would say that it's worthwhile, whatever initialization you're using, to look at initially what are the gradients look like. What do they look like across the layers? Are they super close to 0? Are they way too high? Just to get a sense of whether you're in the good ballpark. So if you're seeing strong saturation, or if you're seeing certain layers that have essentially 0 gradients, you should try something else. Maybe you just change the scale of the, so for instance, this value B, which gives you the scale of the initialization. And I wouldn't be able to speak to whether there are drastically improved ways of initializing beyond this, but I mean, I can definitely believe that there are other ideas that work at least as well. Okay. So now with all of this, we have a bunch of hyperparameters like what is the weight decay factor, what is the learning rate, this initialization, what is the seed of a random initialization, what is the scale of the initialization. So for all of these hyperparameters, we need to find good values for them. And to do that, what we do is we don't find the values that gives us the best performance on the training set, but as in all machine learning, we look at the generalization performance of these hyperparameters, and for that we have a validation set. So another set of data that comes from the same distribution, it's the same problem, but it's not exactly the same examples. Okay? So if you're given a bunch of data early on, we just very early on separate it into a training set and then a validation set, and we also keep around a test set because that's where we measure the final performance after we've found the best hyperparameter. And then how do you search over these hyperparameters? Things that people do often is a grid search. In a grid search, let's say you have two hyperparameters, like the learning rate and let's say the number of hidden units in each of the layers. You would, for each of these, specify a set of values you want to try. So learning rate, maybe I want to try 10 to the minus 2, 10 to the minus 3. And then for number of hidden units, maybe I want to try 100, 500, and 1,000. And then in grid search, I will run experiments for all possible combinations of these values. So, which means 2 times 3, so I'm going to get 6 training runs of neural nets with each of these combinations. And that's one fairly simple approach. One disadvantage of this approach is that it's not very effective because if you have any of these hyperparameters, let's say the learning rate, where you've decided to try one of these values, but that value is just really, really bad. Any neural net essentially diverges, which can happen with learning rates if it's way too high. Then that means that in my example, there's going to be 3 runs that you will have wasted. All of these runs, because they had the bad learning rate, and it was too high, they're all going to give you bad results. And it's also kind of annoying because if, for practically speaking, if one of your neural nets that you're training crashes, then in your grid, in your 2x3 grid, there's going to be a missing piece, and it's kind of annoying that you have never tried this, so maybe you want to finalize the whole grid search. And so a really better approach is to do random search. So instead, what we do is, if we have 2 hyperparameters, we define a distribution or a way of sampling choices for these hyperparameters separately. So maybe for the learning rate, I would sample on the log scale between 10 to the minus 4 and 10 to the minus 6 uniformly on the log scale. And then maybe for the number of hidden units, I pick any integer between 100 and 1,000, maybe also on the log scale. And then what I do for each of my experiments, when I launch them, I decide, so now I can essentially decouple not have any grid and decouple the number of experiments that I do versus the set of hyperparameters I would like to try. So maybe I run, I can decide, okay, I'll just do 5 runs, and then for each of these runs, I sample independently the choices of the learning rate and the number of hidden units. And then I move to, and then I do this separately for all of my 5 runs, and I wait for them to return, and I have my numbers. And then if there was one that actually didn't return because there was a crash or anything like that, then it doesn't matter. I just have one less number, but I don't have this hole in the grid search. So really the better recommended method would be to go for that random search. It's still annoying in the sense that you have to specify good ranges of the hyperparameters, and if you're off, then you might need to revisit what is the distribution you use for these hyperparameters. So oftentimes you would try sort of fairly wide, reasonable ranges, and then you'd run a few experiments, then you look at them, and you're like, oh, maybe I want to zoom in to closer to a learning rate that's 10 to the minus 3. And so maybe I sharpen, so that I take a smaller interval of my uniform distribution over these. And oftentimes we tend to iterate a little bit like this. And there are smarter ways we can use machine learning to do this. There are methods like Bayesian optimization, for instance, that allow us to do that. But already random search is a very good, easy method to try out. Okay. For the number of epochs, the number of times you're going to train on your examples in your training set, one method that is quite convenient is called early stopping. So for early stopping, actually what you do is that as you continue training, you're going to track what is the performance, not just on your training set, but also on your validation set. And sort of machine learning, common knowledge tells us that what we expect is early on we're going to be in the so-called underfitting area where training on the training set gives better performance on the validation set. And then eventually we'll start essentially fitting what are maybe noise or sort of particularities of just the training set that doesn't allow us to generalize to new examples. And that's where overfitting will kick in, and then you'll see normally the validation set performance start getting worse or maybe flatten. And so for the number of iterations, what we would just do is once we reach that point, because we're tracking the performance every certain number of epochs or updates, then we would just detect did things get worse. I might use a look ahead and just wait a few more iterations and sort of measure my validation set performance a few more times. And if it doesn't get better, then this would indicate, okay, I want to stop. And maybe at that point, you just want to have saved the model that you had at this point here, at the sort of best compromise between underfitting and overfitting. Okay, so for the number of updates that you're going to do, instead of just doing a random search, doing something like overfitting is a better approach. I'll go over a few other sort of, what we often call tricks of the trade, so things that are kind of common knowledge that tend to be tricks that work pretty well in having better success with neural nets. One of them is actually to pre-process your data and normalize it. So for real value data, typically what we will do is we will subtract the mean. We might divide by the standard deviation of each dimension of my input vector. This will facilitate training, and oftentimes it actually speeds things up, and you will converge to a good neural net much faster. Mentioned about decaying the learning rate and using this strategy where when the performance is not improving on the validation set, to take your current learning rate and multiply it by a factor, 0.5 or 0.1, decreasing the learning rate drastically, continuing training, and then waiting for things to get worse or not improve, and doing that a few times. So this kind of schedule allows us to start with a more aggressive learning rate initially, and then when we get closer to a trained network, to make much smaller adjustments to the neural net. And that tends to work well in practice. I mentioned using mini batches instead of single examples. One of the benefits of doing that is, well, first we're aggregating many gradients on many examples. So this gives us a gradient where it has smaller variance, so the updates are less noisy. Another thing is that it leverages our hardware better. It turns out that when I'm computing the forward pass and the backward pass of a neural net, I'm essentially taking a vector, say, of the input, of the activations, and multiplying by matrices. And now it turns out if I have a mini batch, I can, instead of doing multiple multiplications of one vector and a matrix, I can do a matrix-matrix multiplication. I can have the whole forward pass being done in essentially one pass by having matrices fed as input to the neural net instead of vectors, where essentially each of the rows or each of the columns of my input would be a different example. And these matrix-matrix multiplications are much more effective than doing multiple vector matrix multiplications. So it's a better way of leveraging our GPU, for instance. You can use an exponential average of previous gradients, so this kind of momentum approach where the update descent direction or ascent direction at the next state is at the current step is going to be my gradient for my current mini batch or example plus a fraction of the previous direction that I used. So there you're sort of accumulating gradients across time steps, which means that when the gradient is always positive for certain parameters or always negative, then it's going to go even faster in those directions. Whereas if they tend to sometimes be negative and positive, this kind of indicates that maybe this is not a parameter, maybe this is not a direction you want to move fast. So this kind of implements that intuition well. And then, oftentimes people will use some of these better formalized approaches for having a per parameter learning rate. So for instance, AdaGrad is one where the learning rate at a given parameter is going to be the learning rate divided by this factor here, where this factor is just the cumulative sum of the square of the gradient for that parameter. So in other words, if you have a parameter that has had a lot of gradients so far, its learning rate is going to shrink faster. And then RMS prop is a version of that where instead of taking a strict sum, we're going to take a exponential sum where we take a fraction of the previous sum of squared gradient times 1 minus that fraction of the square of the gradient for the current mini batch or the current example. So this allows for a learning rate that can, so essentially this term here will always get bigger. So the learning rate will always be divided by a much larger term. Whereas in this case, because it's an exponential average, moving average, then what we get is a learning rate that will sometimes be divided by a large term, but as soon as the gradient becomes close to 0, then you will slowly start dividing by a smaller term, so you will essentially be allowed to go again faster in that direction for that parameter. And Atom, which you might have heard of, is kind of a combination of some of these ideas. I won't go into the details of it. I wouldn't be surprised if this was covered this week in the optimization class. And oftentimes in these libraries, it's sort of implemented for you to use. Finally, I want to say that even though there's TensorFlow and PyTorch and a lot of these will come with built-in components for all of these things that I've talked about. Sometimes in your research, you will want to implement a new component. And for that new component that you want to insert in a neural net, you will need to implement the gradients yourself. And when you do that, you need to check for your gradients because you might have introduced a bug and actually badly implemented the gradient of your component. And the way to do that typically is that we will use a finite difference approximation of the gradient. That is, we will do a forward pass where we've added epsilon to the parameter, and then we'll do a forward pass when we subtracted epsilon to the parameter, and then I will essentially look at the difference of the two losses divided by 2 epsilon. And this epsilon, if it's small enough, that essentially corresponds to the definition of the partial derivative. So we essentially approximate the definition of the partial derivative by a finite epsilon, usually around 2 to the minus 6 or 10 to the minus 6 or something like that. And now if that number is close to the number that your code is giving you for the gradient on parameters, then that suggests that you probably didn't introduce any bug in your calculation of the gradient. And I should say it's not sufficient if you implement a new component, you implement the gradients for it, it is not sufficient to see, oh, the losses are actually going down, so my gradients are probably fine. Neural nets are surprisingly resilient to bugs in the computation of the gradients. And in fact, you only need a few components that have the correct gradients for most of learning to occur correctly. It will almost kind of adjust to the noise that corresponds to the weird gradients that are coming in from other components. So it's really important to also do this. I mean, it's great for engineering that they're robust to certain bugs, but for science, it's not great. So, if you want to publish a scientific result and say that your component really works, you really need to do this. And then finally, another way of debugging is to actually do some training on a very small version of the data set that you want to work with something like 50 examples. So this allows you to detect cases where actually training is not progressing. So if the training loss is not making any progress, well, maybe your units are saturated and you should revisit the way you initialize your weights. If the training error is bouncing up and down, maybe that suggests actually that's kind of a good check for whether your initial learning rate has a good value. And again, not a replacement for gradient checking. These might pass, but your gradients might still be wrong. But it's convenient, it's sort of easy to set up. You just take a subset of your data, you look at your learning curves, and if they make sense, if you're able to reach perfect training error on your small training set, which you should expect if your neural net is big enough, that's already a good sign that you have a good initialization and you are ready to launch experiments on a much larger version of the data set. Okay, any question on these various tricks that I mentioned? Yeah.
In the early stopping, could you go back to the slide for your chance? So on the x-axis, you have the number of epochs, but shouldn't it be the number of iterations? Does it matter?
It's, whatever you choose as oftentimes in fact, so epochs is over the whole data set. If your data set, that's at least, I think people have maybe sometimes different definitions for epochs, but for me an epoch is the whole data set. If your data set, your training set is really, really big, it's okay to just be like, well, actually I'll measure my validation set performance every time I go 1/10 through my data set. As long as you define reasonable iterates that are not too long, because you want to get a signal as to whether you're improving, I don't know, if you have a really large data set, it'd be nice to kind of know every hour or every few hours. The ideal case, you get it much faster, but if your training data is too large, then that you might be forced to only check every hour. But here, instead of using epochs, you can define like a number of updates, essentially, instead. Yeah?
If we use momentum methods such as pattern, does it make sense to use the learning rate schedule?
Yeah, combining momentum with a learning rate schedule is, I think, oftentimes what some people do. These combinations of tricks, you should consider, let's say, oftentimes people start with Atom. I think it's a good sort of first thing to try. It's better than regular gradient descent oftentimes. If you're having a hard time with that, I would then suggest trying to play with a schedule of the basic learning rate of Atom. That's not a bad idea either. I'm sort of giving you a space of things to try out where you're having a hard time training your neural net here. And it is going to vary a little bit from problem to problem. It's a good compromise between simplicity and effectiveness, random search. So Bayesian, it's just, if you have access to a Bayesian optimization system, then, you should definitely use it. But if you don't, then just implementing random search is like a really good way to start. Don't do grid search, essentially. Yes? When, sorry? Oh. So what would I normally debug in a small data set? I will essentially look for these. So essentially, it's kind of a unit test. If I don't reach perfect training error on my small training set, especially for classification, there's something fishy going on. I should be able to classify perfectly my data unless there are two exact copies of the same input with different labels. Otherwise, you should reach perfect. So if you're not able to do this, there's something wrong maybe with the initialization, maybe with your choice of optimizer. That's kind of, you want to achieve this. You can't really debug for things like, is it generalizing properly? On a small data set, it will generalize very poorly, but you do expect to overfit. So the first check is to make sure that it can reach the capacity required to fit a small data set, because it should always do. Like 50 examples, it should always be easy to overfit. All right. I am totally confused by the timer, by the way. It says 13 minutes. I have until, what, 11:30?
So we're going to take a break.
Oh, you want a break? Okay.
So
Yes?
thanks, Hugo, for the first part of your talk.
Sure.